Today, I'm very pleased to welcome back Dr. Chris Miller, who's the Eurasia Program Director at the Foreign Policy Research Institute. Chris gave a talk here to the lab last December on his book on Russia's aspirations in the Pacific, but his CGSR lecture this morning is on his new book, just coming out this month, titled Chip War, The Fight for the World's Most Critical Technology. We're only going to go for an hour this morning, so I'm going to dispense with the normal teeing up of the presentation. Everybody knows how topical this presentation is. It's in the news all the time. Chris has been in very high demand the last few weeks. He's given a lot of these talks over the last few weeks on his book. It's the #1 bestseller in national and international security on Amazon. So I'm just going to introduce the speaker and let him get underway. So in addition to his duties at FPRI, Dr. Miller also serves as Assistant Professor of International History at the Fletcher School of Law and Diplomacy at Tufts. He's the Jeane Kirkpatrick Visiting Fellow at the American Enterprise Institute, and he's Director at Greenmantle, which is a New York and London-based macroeconomic and geopolitical consultancy. He's the author of 3 previous books: Putinomics, The Struggle to Save the Soviet Economy, and We Shall Be Masters, which is what he gave a talk about here at the lab late last year. He frequently writes for the New York Times, the Wall Street Journal, Foreign Affairs, Foreign Policy, the National Interest, and other outlets, sort of everything that matters on foreign policy. A lot of recent stuff on Russia that's worth checking out. And he has received a PhD in history from Yale University and a BA in history from Harvard University. The ground rules, as always, Chris is going to talk for about 25 to 30 minutes, at which point we'll open the floor up for discussion. Get your hand up electronically, submit your questions to me in the chat function, and we'll get the discussion rolling in the time we have allotted. Chris, thank you so much for being with us here today, and over to you for your remarks. I'm going to go ahead and put a link to your book in the chat function while you get started here. Thanks so much.
Great. Well, thank you very much, Michael, for the introduction. I'll put up some slides to guide our conversation. Let me just say at the outset what a pleasure it is to be talking with this particular audience. When I speak with many audiences, the first question is, what actually is a semiconductor? But I'm delighted not to have to explain that to, I suspect, many of you on this call. And indeed, I came to this topic not planning to write a history of semiconductors at all, but rather planning to write a history about missile technology during the Cold War. And I quickly realized that the really interesting part about missile technology was in the guidance computers, and the interesting story of the guidance computers was how it became possible to miniaturize computing power. And what I found was a story that begins in the Cold War days of the growth of Silicon Valley, but actually was a much more global story than that, a history that stretched to the Soviet Union, which was in the early days of the Cold War trying its own crash program to miniaturize computing power for the exact same reason, to fit in missile guidance computers. But then a story that continued to shape both the global economy and the global political system over the coming decades, all the way up to the present day. And as I began doing this research around 5 years ago, it was just the early stages of the US efforts to restrict the transfer of certain chip technologies to China, with the controls on Chinese firms like ZTE and Huawei. And I came slowly to understand that there was in fact a direct linkage, or a series of direct linkages, between early Cold War missile technology and the US-China technology competition and arms race to some extent today. So that's what I'd like to set out in the next 20 or so minutes. Today, when the typical person thinks about computer chips, they think not about missile systems nor about defense technology in general, but about the use cases of chips across the economy, whether it's smartphones, which consume around a quarter of all chips in terms of dollar value spent today, or PCs or Internet of Things devices. Almost all chips today are used for civilian purposes. Just 1 or 2% of chips by dollar value end up in a defense system. But the origins of semiconductors, as I said, is in missile guidance systems. The first major order for integrated circuits after they were invented in Texas and California in the late 1950s was for the Apollo spacecraft's guidance computer. And the second major order for chips was for the guidance computer on the Minuteman II intercontinental ballistic missile. So from the earliest days of the semiconductor, there's been a really deep relationship between military uses and technological advances. And that's understandable because the military is willing to do things that private firms are generally unwilling to do, which is to pay a lot of money for a small volume production run on an untested or poorly tested technology. That's what integrated circuits were in their earliest days. The integrated circuits that powered the Apollo spacecraft's guidance computer were produced by a completely untested firm called Fairchild Semiconductor. And so you'd never run a commercial operation using such untested technology, but I guess it was trustworthy enough for NASA to send 3 astronauts to the moon. And so that's why there's been this deep connection between defense spending, government-funded R&D, and advances in chip technology. And of course, even today, in fact, especially today, there's a whole lot of chips in defense systems. And the number of chips in each specific defense system and the type of chips is often hard to ascertain because a lot is classified. But it's no surprise, I think, to anyone on this call that semiconductors are crucially important for the processing power, for the memory, for the signals processing, undergirding all sorts of defense systems. So just to give one example, the Javelin anti-tank missiles that have been in the news recently because the U.S. has transferred many to Ukraine have over 200 semiconductors inside. And of course, this is an old technology by the standards of defense equipment, several decades old. And so newer technologies are even more reliant on the types of processing power and signals processing that semiconductors enable. And when you look at visions of the future of warfare, like this diagram produced by DARPA a couple of years ago, they're envisioning an even more interconnected battle space with more communications, more sensors, all networked together, sharing more information than ever before. And all of that is a question of getting larger numbers of more powerful semiconductors in more types of systems. And so both in Washington and in other capitals in the world, defense planners realize that semiconductors will be a crucial determinant of military power, and perhaps the crucial determinant of military power over the coming decades. And I think you could really argue that over the past couple of decades, they've been the crucial determinant of military power as well. And so when you look at Chinese systems, there is a great focus in Chinese literature on applying artificial intelligence to military systems. And of course, this is first and foremost a question of getting enough computing power in military systems to enable them to undertake the processing necessary. And of course, it's one thing to do this in a data center. It's something else to do it in a device that's flying around and facing space constraints and power constraints and all sorts of other constraints that you face in a military system. And so having more advanced semiconductors that can do more, taking up less space and consuming less power is crucially important for this type of use case as well. Which is why we see semiconductors now more than at any point since the 1980s playing a major role in both US politics, Chinese politics, but also Japanese, European, Taiwanese, Korean policy, because political leaders around the world are coming to realize in a way they haven't really realized since the days of the Cold War, the extent to which semiconductors undergird not only economic influence or technological capabilities, but also military power. And in the United States, over the past several years, there's been a substantial recommitment from the U.S. government towards investing in microelectronics technologies. And you can date this really back almost half a decade now. The Chips and Science Act was just passed, of course, and is being implemented as we speak. But over 5 years ago, the Defense Department's Advanced Projects Research Agency, DARPA, unveiled its Electronics Resurgence Initiative, which was designed to pour substantial new sums of money into chip research on the argument that new types of semiconductors and new capabilities that semiconductors would enable would be important to the future of military power. And Congress over the past half decade as well has been in different ways pushing forward pieces of legislation designed to push forward US semiconductor innovation and also restrain the ability of China to access technological advances elsewhere. But of course, the centerpiece of this is the Chips and Science Act that was just passed, which will spend almost $40 billion subsidizing the creation of advanced manufacturing facilities in both logic and in memory chips in the United States over the coming 5 years, which is going to have a meaningful impact on reducing the U.S. reliance on importing leading-edge chips from abroad, largely from Taiwan in the case of logic, or Korea in the case of memory. Of course, we'll still be quite reliant on Taiwan and Korea, but somewhat less so than we are today. And today, just to put some numbers out there, Taiwan produces 90% of the most advanced processor chips, and Korea produces almost half of memory chips. So there's a really extraordinary global reliance on these two geographies, which is understandably, I think, made some security-minded officials in the United States nervous about the implications of that. Finally, the U.S., as recently as last week, has been dramatically intensifying controls on the transfer of technology to China. And just last week, the United States rolled out a series of new restrictions banning the transfer of advanced graphic processor chips called GPUs to China, which are used in data centers for artificial intelligence applications, banning the transfer of certain types of chip making equipment, the ultra-precise machine tools, in this case for deposition of fine, thin films of materials on silicon wafers, banning the transfer of those types of tools to China, banning the use of any sort of U.S. equipment in certain Chinese supercomputers, and then also, most surprisingly, I think, banning any U.S. person, so a U.S. firm or a U.S. citizen, in working with a huge swath of Chinese chip firms. So it's really a full-scale assault on China's ability to modernize its own chip industry, and it's likely to set China back for some amount of time, because you can't operate an advanced chip-making facility in the world today without using U.S. tools and equipment. So that's the U.S. strategy. Invest more in R&D, invest more in advanced fabrication, and try to restrain China in the process. And China, of course, has got its own strategy predicated around the thesis that pouring many, many billions of dollars into its semiconductor industry will help catalyze new advances. And although we in the U.S. have focused on the CHIPS Act in the United States, in fact, China has been at it for many years now via a national integrated circuit fund, commonly called the Big Fund, which I guess gives you a sense of its size. That is at the national level investing in semiconductors, and then a series of comparable funds at the provincial and local level that have poured many tens of billions, and probably over the past decade in the low levels of hundreds of billions, into the semiconductor industry in China, trying to build up capacity and also build up technological capabilities domestically in China to reduce reliance on the United States. And for the Chinese leadership, this is important because today China spends more money importing semiconductors than it spends importing oil. It's the greatest vulnerability that China faces in economic terms, but also in political terms, because China is hugely reliant on chips imported from the US, from Taiwan, from Korea, from Japan, none of which China has straightforward commercial relationships, all of which it has very complicated geopolitical relationships with. And China's industry depends on these chips because Chinese firms are still far behind in most parts of the supply chain. And if you look at what it takes to produce a advanced chip, what you find is that although the United States is now a second-tier producer of chips themselves, it still has a dominant position in the semiconductor supply chain. And here I'll pause for a minute to explain what it takes to create an advanced semiconductor for those who are not familiar. First, there are a set of software tools called electronic design automation tools, or EDA tools. There are basically three companies that dominate this sector. All of them are in the United States, and you need this specialized software because an advanced chip could have, in the logic space, could have multiple billions of components on it, 10 billion transistors, to take an example of a chip that you might find in your iPhone. And to lay out all these transistors on a small piece of silicon requires really complicated software. When the chip industry first launched, laying out chips was done by hand because you were mapping just tens or a couple hundred of transistors. But now in the days of tens of billions of transistors, you need software to do the layout for you. So that's the first step in the process, is to acquire the software, and almost all the software is in the United States. The second part of the process is to acquire intellectual property from a variety of different companies, because today most chips are not just designed by one firm, but involve pieces of intellectual property from multiple different firms. And this too is a part of the industry where the United States is very influential, and the UK also is home to a firm that has a lot of the core intellectual property around which many chips are designed. Once you've got your chip design, you need to acquire a silicon wafer. Ultra pure silicon is needed. Silicon is one of the most commonly distributed elements in the Earth's crust, just sand. But you need to purify the silicon to an extraordinary degree with basically no impurities whatsoever. And there's only a couple of companies that can purify it to the requisite level of purity. And then one of the most complicated parts is acquiring tools used to etch tiny holes in the silicon, or to deposit thin films of materials onto the silicon, or to imprint patterns using light onto the silicon. And the market for tools used in the fabrication process is really dominated today by just 5 companies, 3 based in California, 1 in the Netherlands, 1 in Japan, which have sort of an oligopolistic hold on the market. And they have this hold because they've been in their market positions for decades, in some cases almost half a century, and they're able to do things with their machine tools that no one else can. Just to give you an example of the most complex example of machine tools used, the advanced lithography system that produces extreme ultraviolet light, which is used in the making of advanced logic and memory chips, is produced by ASML, a company in the Netherlands. Each tool costs $150 million a piece, and this tool took 30 years to develop and billions of dollars in investment. It involves some of the flattest mirrors ever made in human history, some of the strongest lasers commercially deployed, explosions at hundreds of thousands of degrees Fahrenheit happening on a regular basis inside of a machine. So the engineering involved is truly extraordinary. The number of component parts in these machines is in the low millions. The company actually doesn't know how many component parts there are in its machine. I've asked. They know that in just the laser portion of the machine, there's 457,000 component parts, and that's just one of the key components. So there's certainly over 1 million involved, and replicating this machinery is basically impossible. Perhaps it could be done in a decade's time at extraordinary cost, but no one is going to do it in a commercially viable way. So the 5 companies that control the fab tool market have very, very strong market positions. You need these tools to make chips, and no matter where you make chips in the world, you rely, if you're producing advanced chips, on tools from these 5 countries. Whether in Taiwan or Korea or the United States or Japan, you must import tools from these countries. After you got these tools, you actually do the fabrication process. You take your design and you etch it onto the silicon chip, and then finally you package it and test it and make sure it works properly. And when you add up the different parts of the value chain, what you find is that although the US only produces 10 or 15% of the world's chips, it produces 39%, according to this Georgetown University estimate, of the value in the typical semiconductor made, followed by South Korea and Japan. And a number of key choke point technologies are made in the United States by US firms, especially in the software tools and the machine tools. And what that means is that the United States has the ability to cut off other countries from producing advanced chips by limiting their access to machinery. And indeed, the US can stop other countries from producing chips for third parties, because any fab in the world that's producing anywhere near the leading edge has to today use US machinery or US software. And this is a extraterritorial power the US has used increasingly against China, most recently with the regulations announced last week that prevent chip facilities in Taiwan or South Korea, for example, from supplying certain types of advanced chips to China, and threatening to cut off access to machine tools if they don't comply. So this is a problem for China, which has a desire not only to produce low-end chips, but also high-end chips. And it's a problem that China is going to struggle to get around. Today, China has a small amount of logic chip making capacity that's somewhat close to the cutting edge, though not at the cutting edge. It's got a much larger amount of capacity on the lagging edge of the logic spectrum, and it's investing very, very heavily in this space. So commercial estimates like this one suggest that China might end up playing over 20% of the overall manufacturing capacity base by 2030, almost exclusively in the low-end, low-tech logic segment, and a bit in less sophisticated memory chips. And this will change the geography of the industry, even if it means that China stays far behind where the cutting edge is today. And as the United States intensifies its technological restrictions on China, and as China doubles down its efforts to find alternative means of acquiring the technology that's relevant, either by producing it domestically, though that's hard, or trying to acquire it surreptitiously from third parties, there's a risk that the tech restrictions intensify the geopolitical confrontation. There's already plenty of allegations from the US that Chinese firms have been violating existing rules, and we've seen a small number of Chinese officials discuss whether China might try to increase pressure on Taiwan, or eventually even use its military against Taiwan to induce Taiwan to loosen chip rules and thereby gain access to Taiwan's advanced production facilities. At this point, that seems something that's not that plausible, but as the military balance continues to shift in China's favor in the Taiwan Straits, China's leverage in this sphere is likely to increase. And indeed, I think we should assume that U.S. restrictions on China continue to increase as well, with the announcement last week not being the last likely announcement in terms of tech restrictions on China. So this is going to have a dramatic effect on the U.S.-China relationship, but also on the structure of global semiconductor supply chains, which are today one of the most complicated and internationalized supply chains of any product that exists. Making an advanced chip is so hard, it requires such advanced machinery, such precision, that you can't make a chip today without acquiring machinery and materials from multiple different countries, at least from the US, from the Netherlands, and from Japan, are countries that you can't get around if you're making an advanced chip. And the supply chain in general is beginning to shift under the pressure of US-China competition. For one thing, the most advanced chip maker in the world, TSMC, is for the first time really beginning to diversify its production base away from Taiwan. Today, all of TSMC's most advanced chips are made on Taiwan. Over the next coming years, they're going to open up new facilities in the US, in Arizona, in Japan, and then probably also in Singapore and somewhere in Europe as well. And this will have some impact in reducing their reliance on Taiwan-based production and the world's reliance on Taiwan's produced chips. We'll still be quite reliant on Taiwan, but less so than we are today. Second, we've seen a dramatic expansion of the export controls on machine tools necessary to make chips. And it will be a long time, if ever, before China acquires some of the most sophisticated tools needed to make advanced chips, like EUV lithography equipment, which has been banned from buying. And this is a real problem for China because making this equipment on its own is going to be brutally expensive, if indeed it's possible at all. Third, the US has made clear it's no longer willing to assist in any way any advances in China's chip industry. The US has put a complete ban on the use of US software in any sort of post-FinFET transistor architecture, which is the next generation of transistor architectures. And more than that, it's banning use of the transfer of machine tools, even for less advanced production nodes. So it's really trying to stop China's technological advances in its track. And this policy was explained by Jake Sullivan, the National Security Advisor, a couple weeks ago as a shift from prior policy. In the past, the U.S. had tried to keep China a couple generations behind. Now, Sullivan says the U.S. policy is to grow the gap between the U.S. and China, partly by running faster on the side of the United States, by investing more R&D, but in no small part by halting the ability of China to take advantage of foreign machine tools and foreign software as China produces its own chips domestically. And although China will face dramatic restrictions on its ability to produce advanced chips, it's still got a lot of capacity to produce less advanced chips, and it's going to spend tens of billions of dollars building out capacity in less advanced chips, which are going to have a vast impact on the semiconductor market, regardless of China's ability to produce advanced chips. This will threaten the profitability of foreign firms because China will be able to sell at below market prices, and I expect the next couple of years will be dominated by trade disputes and anti-dumping negotiations over whether or not Chinese chips produced thanks to government subsidies should be allowed in foreign markets. This is something that is a great concern to chip firms because it threatens their profitability quite directly. And then fifth, on the space of memory chips, where China seemed to be advancing quite rapidly, it almost was at the point of commercial viability in the case of the most advanced Chinese memory firm YMTC, which as of this year, Apple was exploring as a potential supplier for NAND chips in its iPhone. But as of last week, the US is imposing quite tough restrictions on YMTC, and its ability to move forward technologically now looks very much in doubt. So both in the logic space and in the memory space, China appears, at least for now, to be frozen in place until it can try to develop domestic replicas of the tools in questions, which is something that will take, I think, many years to do. So what is the impact of all this going forward? Well, one, for the industry itself, there's a real change to the market dynamic. Over the past couple of decades, government subsidies have played a comparatively minor role in the industry, and private sector investment has been the key driver. That's now changing in every single country that matters. The United States, Europe, Japan, Taiwan, Korea, and above all, China are pouring billions of dollars into building out fabrication capacity, which risks overcapacity in the industry and therefore risks moving the industry away from a market focus towards a much more securitized, state-driven focus, which will be the only way to deal with this type of overcapacity if it emerges as expected. You can just see the dramatic increase in capital expenditure over the past couple of years. We're now pushing twice the level of capital expenditure this year than we saw in 2020. And it's unlikely that the market is going to be able to consume all of the chips that will be produced, especially in the lower end logic segment of the market where China is investing most heavily. Second, for supply chains, every company is now thinking seriously about what this partial decoupling means for them. For a long time, the chip industry didn't think much at all about geopolitical issues, but now it's having to rethink the way the supply chains are structured, and anything passing through China is increasingly seen to have a lot of regulatory risk around it for good reason. And then third, China's own drive for chip self-sufficiency will be incredibly expensive if indeed it's pursued over the course of many years. We already see special government funds, denoted here in green, making up a surprisingly large portion of China's overall government debt. It's large enough to be graphed by the IMF when they add up China's total government debt stock. And the more China invests in the semiconductor industry, the more this green part of the graph will grow over time. And the chip industry is one of the most expensive industries to build, requiring tens and tens of billions of dollars of capital expenditure each year. And if China wants self-sufficiency, it's going to take a lot of time and going to be very, very expensive. So conclusions, what does this mean for the electronics industry? What does it mean for national security? First off, anyone who thinks that semiconductors are mostly about smartphones or mostly about PCs isn't listening to defense officials. And it's taken a long time for the industry to realize it. But the reality is the security-focused officials are winning a much bigger say over how the industry is structured relative to even 5 years ago. Second, tech policy in all of the key capitals, Beijing, Washington, Tokyo, and others, is only going to get more securitized over the coming years as this bifurcation continues and deepens. And third, I think the tech industry in general and the chip industry in particular is rethinking what globalization means. For a long time, the line from industry has been that self-sufficiency is a naive idea, that it's simply impossible. And that's probably true, but the reality is that every segment of the industry is thinking a lot more about ways it can limit supply chain risk and ways it can reduce its supply chain dependencies on China than ever before. And this politicization of supply chains is a process that I think has only just begun and will have impacts in how we actually produce the semiconductors we rely on for many years to come. So I'll stop there, but would welcome any questions or comments that you have.